All right. So we're going to go ahead and get started then. So good morning. My name is Heather Robbins. I'm the Director of Communications here in the Eberly College of Science. And I have the honor and privilege of welcoming you to the fourth week of our 2026 Ashtekar Frontiers of Science lecture series. This popular public winter series is now in its 32nd year. We're so excited to have you here. The lecture series was founded by a Ashtekar who is with us here today in 1995. Yes, thank you. In 1995, soon after he arrived at Penn State as director of a new research center that subsequently evolved to become the Institute for Gravitation in the Cosmos. It owes its success to tireless efforts and meticulous planning by Barbara Kennedy, who presided over the series during its first 25 years, making it one of the most successful science outreach events in central Pennsylvania. This year's lecture series, titled Unexpected Pairings, addressing today's biggest societal questions using different disciplinary approaches, will explore how researchers in the college approach some of today's biggest societal questions using different approaches. The 2026 lecture series brings together researchers from disparate disciplines to showcase how faculty from across the college's 7 departments leverage wide-ranging methodologies and theoretical approaches to tackle pressing scientific issues and help shape the future of science, health, and humanity. Each of the 6 lectures has and will feature 2 high-level overview talks focused on one of the big societal questions that drive research in our college. Today and for the next 2 Saturdays, you will hear from researchers on topics, or have heard from researchers on topics, including origins, medicine, materials, climate, and education. If you missed one of our previous weeks, you can find the recordings of those online. So even last week's is online already at science.psu.edu/frontiers. Today's first lecture topic, building quantum materials from atoms and light, is being presented by Bryce Gadway. Gadway is a professor of physics. His research specializes in experimental atomic, molecular, and optical physics. His research group specializes in developing new experimental techniques for ultra-cooled atoms and Rydberg atom arrays, using these systems to explore novel transport behavior and collective phenomena. And the second lecture topic, I'm going to introduce her now, but she'll be coming up after Bryce, is utilizing electron microscopy to reveal the atomic frontier. Will be presented by Danielle Reifsnyder Hickey. Danielle is an assistant professor of chemistry, material science, and engineering. Her research group is currently investigating the atomic structures of nanomaterials, two-dimensional materials, and emerging materials for applications in electronics, energy, and health. Following the lecture, graduate students Matthew Krebs and Ethan Springhorn will lead a moderated question and answer session with Bryce and Danielle. So I'm going to ask you all, if you haven't, please get your cards, even if it's not a winner anymore, and write down your questions throughout both lectures. And then after the second lecture, our wonderful undergraduate Science Line Pride students will come and collect your cards, and they'll bring them down, and we'll go through that moderated Q&A. So without further ado then, welcome Bryce.
Okay, thanks Heather, thanks Michelle, and thanks Abai for founding this many years ago. Okay, so this is a picture from our lab of our material that we make, and I'll spend the rest of the time kind of telling you a little bit about this and starting with a bit of a primer on quantum physics as well. So what you're seeing here is a picture of light collected from a bunch of atoms that we have held in a vacuum chamber by tiny little lasers, and that actually can talk to each other by exchanging photons. So this is a material that we use. It's kind of a weird thing you can't put in your pocket, but it has real world impacts now in a lot of companies around the US and around the world trying to make quantum computers and quantum simulators. So before telling you more about those materials, these are the people that do the building in our lab. So Matt and Ethan, who are here, I owe you a beer. Thanks for giving up part of your Valentine's Day for this. And then a whole bunch of other folks working in the basement of Davy Hall, Davy Laboratory, building up these atom array experiments and some other experiments with gases of atoms at kind of nano-Kelvin temperatures. And we've been here for just a few years, moving over from Illinois back in 2023 after the pandemic. So this is maybe a little bit of a kind of a timeline for the talk. So I'll start with a primer on quantum mechanics, which is pretty central to understanding how our materials works and kind of how we build them as well. So I'll start with the question of what is quantum? And some of the aspects of this are kind of in the name. And some of the earliest evidence for quantum behavior of our universe came from looking at tiny things like atoms and seeing quantized or discrete emission spectra from things like hydrogen. So you'd put some atoms in a lamp, run high voltage across it, excite them, and look at the light emitted. And instead of seeing the kind of continuous spectra you would see from a thermal light bulb or the sun, you would see these discrete emission lines. And this comes from the fact that the atoms have kind of discrete levels or states that the electrons in them can occupy. And that if I excite the atom by exciting the electron to one of these higher levels, they decay, and in this decay, they emit light or photons of different colors. And the colors are kind of dictated by how much energy the light has when it's emitted. And so, this really kind of transformed the way people thought of atoms. Niels Bohr had a somewhat accurate picture where you had kind of a planetary picture of discrete orbitals that the atoms could take, that the electrons could take, but it wasn't really well motivated why they had particular values of the energy. And then a PhD student, Louis de Broglie, had a nice kind of conjecture that maybe the electrons actually behave like waves. And just like the kind of waves or regular standing waves we have of, say, people kind of shaking a string, that only certain length scales of the excitation or wavelengths are allowed as kind of stationary solutions to wave equations. And so this is a picture of an electron kind of going through a certain number of periods or of wavelengths as it goes around an atom. And so just a few years later, this was confirmed in the US at Bell Labs, at modern day Bell Labs by Davison and Germer. And nowadays you can do some really sophisticated versions to confirm the wave nature of matter by taking things like electrons and actually doing what are called interference experiments or diffraction experiments in the same way we can do this with light by making kind of cold or coherent beams of electrons, shining them onto some grating. So when this was first done, it was actually done just by shining them on atoms and looking at diffraction from crystals. And you can actually make gratings where the separation is many thousands of atoms between two slits. And if you look sort of very far away, you actually see patterns like this, where all these sort of points where it's bright is where you get lots of electrons, a large flux. These darker points are where you get interference that comes about from kind of possible pathways where individual electrons could go. So an electron kind of has some probability to actually go through this side and go through that side. And it's in a superposition or some sort of unknown state of which slit it actually goes through. And what's amazing is you can actually see this build up one by one. So you shouldn't think of this as a field like a laser field or water waves where different particles can actually interact with each other. But even at the point of seeing individual electrons come by, you can see this interference pattern build up one by one. It's not just for the tiny elementary particles, but people have done this now with things like buckyballs, which have an allotrope of carbon with 60 atoms, and even little nanoclusters that have 7,000 atoms that are approaching the size of viruses. So it's pretty amazing to think that things on the size of nearly living species could be in superpositions of being in multiple places at once. And from this kind of picture, you see another aspect of quantum mechanics that's pretty central to it, that it's probabilistic. So this kind of pattern over here tells us about the probability, essentially, of where we might find the electrons. But every time one electron goes through this kind of pattern, it shows up somewhere. And we can't predict ahead of time where it will be. We can say it won't be here because there's something called destructive interference. So interference from these pathways, but it could be here or here, or anywhere where we have bright spots. And the equation, something like the version of Maxwell's equation that tells us how quantum particles evolve, tells us only about the probabilities of what we might measure in some experiment. And one of the most striking aspects of quantum mechanics comes when thinking about measuring systems that have more than one particle, and how the outcomes of measurements on the two parts of a system can actually be correlated in some way that's very different from what we find in the classical world. So this is called entanglement. It means that the outcomes of different things might be entangled with each other, sort of tangled up. And so we can imagine something like a photon, this red dot, emitting two two light pieces of light, something called photons. This is like an elementary particle of light. And this can happen when we excite an atom and have it decay through different energy levels, emitting 2 photons. And we might write the state like this. What this is telling you is that we sort of have 2 possible outcomes where the polarization of this light, this is a property, it's useful for things like sunglasses developed by Polaroid, having being sensitive to the polarization of this light, can have 2 outcomes, and that if I measure path 1 and path 2, the outcomes of measurements are going to be perfectly correlated. So if I see that the light in this path has a particular polarization called right, I'll find the same polarization in this path. And so this is a funny thing. It actually kind of, maybe not puzzled, but maybe made Einstein really suspicious about quantum mechanics, that it actually implies that if I allow these pieces of light to separate by sort of light years, that I could measure one of the particles and then, seemingly actually influence the outcome of a measurement far across the universe where no signal can possibly move between them. And so he called it spooky action at a distance. And so you might think there are also classical ways in which things can be correlated. So if I have $100 in my pocket and I give $51 to one of my children, the other one will get 49. Or if I have a kind of aloof scientist who always wears mismatched socks, if I find that one foot has a pink sock, the other one will surely not have a pink sock. But it was shown in the 1960s that one can actually kind of work through the math of what quantum mechanics predicts and show that it is measurably different from what you would get in classical system. This was done by John Bell, leading to kind of really a celebrated result in quantum theory. Okay, and so this kind of property, it's weird. It's a weird aspect of quantum mechanics, but it's also useful. And so in quantum communication or quantum networks, it's used to teleport information where you can kind of send states, send quantum states across different systems without actually sending a particle. Not quite humans yet, but maybe small things. And it's really a central ingredient to a lot of the applications or industries that are rising up over the past decade or so. So things called quantum computing, where one can make computers out of, instead of digital logic like zeros and ones, some more fancy kind of logical elements. This is a picture from Google. Things like quantum simulation and quantum sensing that I'll discuss a little bit in a few slides. And then lastly, not to get too in the weeds, but really kind of the most elementary and maybe the most important for our everyday life aspect of quantum mechanics comes from something called the quantum statistics of particles. And really it just tells us why certain types of matter behave the way they do and other forms of matter behave very, very differently. So it has a huge impact on our everyday life. We have these particles in nature called bosons and fermions, named after these great physicists, Satyendra Bose and Enrico Fermi. And they basically come in 2 flavors. For some of them, they have a property called a spin. It's not that important at the moment, but it takes values like 1/2, 3/2, and values that aren't integers. So electrons, like Danielle will tell you about, are fermions. Neutrons and protons are fermions, and many other composite particles are fermions. The key aspect of them is that they tend to avoid each other. You kind of can't put more than one identical fermion in the same state. And that leads to all kinds of things that we experience in nature. So we get the periodic table. This comes from the fact that as I build up atoms and I try to put more electrons in, I can't put 10 electrons in the lowest energy level of something like hydrogen, but they have to kind of stack up, and I get different elements like lithium, sodium, gallium. It gives us the property of all kinds of materials like metals and insulators. So salt and copper behave very differently. One conducts electrons, one is an insulator, because of basically how electrons behave in the system, that they have to occupy and fill up energy levels from the ground up, or they have to avoid each other. And it tells us why things like neutron stars don't just collapse into black holes, but there's some pressure that keeps them from sort of just going into larger and larger density. And then important for things like this laser is the fact that light behaves very differently. Light particles are bosons. They have integer spin, and they actually kind of want to bunch up together. So instead of avoiding each other, they want to occupy the same state. This is why lasers have nice properties, why people like Dave and I can make funny gases of atoms that are bosons and form a state called a Bose-Einstein condensate. And actually why superconductors, which are also made of electrons, behave very differently. So these are systems where electrons can flow without resistance. And it's actually because these electrons, which are fermions, pair up together as kind of like a little married couple, and then they act like bosons and flow without resistance. Okay, and then not to muddle the picture too much, but we even have things like anyons. And I bring this up because local celebrity Janendra Jain helped to kind of develop the theory that describes how these really funny particles can show up in lower dimensional systems. Okay, so with a little bit of quantum out of the way, what's a quantum material? Almost everything. So like the wooden desk in front of you is probably a quantum material. This copper wire is a quantum material. In this aspect, I mean that the quantum nature of the things that move around in it, these electrons, is actually really important on the temperature scales that we interact with the system. So it behaves in the way that it does because electrons have the quantum statistics of a fermion. Okay, more up to date, we might think of materials like this. This is one imaged by Danielle and probably built in her lab of, I guess, bismuth selenide stacked between a bunch of different things, where it has some much more complicated properties, probably things like spin orbit coupling and topology that I won't tell you about. But basically, it's a crystal of atoms with electrons that move around between atoms. And so in these materials, things happen fast. So about a billionth of a millionth of a second is the timescale for electrons to move around. That's a femtosecond. Things are packed together at kind of nanometer scale, and so we can't use optical microscopes to look at them, but we need electron microscopes and more advanced sensing. And then we have to cool them down with cryogenics and make them in really clean rooms. So about 30 years ago, there was a field of experimentation that kind of developed where they did something very perverse. Instead of making a material out of atoms and having electrons flow around, they actually made materials out of lasers by using interference of light to create kind of perfect crystals, which this kind of crystal would actually be formed from kind of like intensity maxima and intensity minima of some laser interference pattern. And it turns out you can actually put atoms or many different things inside of one of these crystals, and you can study how the atoms themselves hop around. Very analogous to how electrons move in a material, but sort of blown up by, instead of nanometers to microns, so 1,000 times bigger, or 10,000 times bigger, instead of femtoseconds, timescales, we go to millisecond timescales. So, 1 billion times 1,000 times slower. And you can actually just see things directly under a microscope. So this is a great field of research. And then in our lab right now, we're doing something which is even easier or a little bit more of a cheat. So we go even 10 times larger apart. So here we actually have an array of atoms. Each one's held in a little laser beam that kind of confines it. And they're separated by about the width of a thin human hair. And in this case, the atoms can actually exchange photons. Those are the things that move around in our quantum material. So things are really dilute. Things are actually pretty fast again in this regime. So about 10 to 100 nanoseconds for things to move around. And we cool them actually with lasers instead of with cryogenics. And then this is maybe the most modern kind of quantum material we have. This is a picture of one of these quantum computers again, where it's photons of light moving around between little tiny resonators or boxes that hold photons. And they're kind of in a weird regime where only 0 or 1 photons can occupy it. It's sort of like having a violin string that can either be completely stationary or have a very small vibration. And as soon as you try to have it vibrate more, its frequency changes so much that you can't excite it further. So it's really anharmonic is the word. Okay. So why would one do this? This last picture maybe showed one application. So Google and IBM and lots of people are building these machines with billion-dollar efforts, not just for fun, but because there are real applications in quantum computing. And so again, in these quantum computers, one takes the binary zeros and ones of digital logic and replaces them with something where the states can actually be in one of these quantum superpositions of being both a 0 and a 1. And so these elements are called qubits or quantum bits. And instead of normal logic gates like OR or NOT gates and NAND, you have quantum gates, which actually generate entanglement in the system. And then for certain problems, these can give you a lot of speed up. And so there's a lot of national interest in building these, and now even industrial interest. So it can solve optimization problems. It can factor large numbers. Currently, it's about $1 billion industry per year, and it's projected to be around $200 billion by 2040. So they're expecting a lot of increase both in the capabilities, but also kind of the kinds of problems it can tackle in just 10 years. This entanglement and quantum systems can also be helpful for sensing. And so does anyone know what this picture is of? Probably many of you. It's some people out in a field somewhere in Washington built something to measure gravity waves. And it turns out that by having quantum entanglement in their light, they can actually be sensitive to something like 16 times more black hole mergers and things like this. So quantum sensing in LIGO is one case where we actually get an advantage for having quantum properties of the system. And then quantum simulation is kind of a very particular kind of quantum computer that can solve basically one problem. It solves a very particular problem, maybe relevant to chemistry or physics, and it gives a big speed up. And so this was actually the first kind of quantum material that was proposed by Richard Feynman as something that could be very useful to understand nature. And so after a little bit of swearing, he says, if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, and it doesn't look so easy. And it's not so easy, and people have been doing it. And this wonderful problem is one of the motivations why this is basically what we do. This is the kind of approach we have, and it's more related to fundamental science than an application, but actually understanding more about physics and chemistry through these quantum materials. So trying to discover something new. And the reason we build the experiments to do this is actually classical computers fail to describe quantum systems. It just becomes exponentially hard as a problem to solve on classical computers. So in the last couple minutes, I'll maybe show you how our quantum system works, and then move over to Danielle. So the first step to make our quantum material is to make completely nothing. So we suck all the air, all the everything out of some vacuum system and start with just complete vacuum. And then we add some atoms. We inject some atoms into an evacuated chamber, and we cool them actually using lasers, which you can think of it as kind of like throwing tennis balls at a speeding train that can eventually slow it down, in this case, by sort of bouncing light off of an atom. And we trap them using lasers and magnetic fields. This is a picture of a ball of about 1 billion atoms. This is light that's kind of bouncing off it into some student's camera or cell phone these days. And it glows red because it's rubidium, so it looks a little bit like a ruby. And then this is rubidium at kind of standard temperature and pressure, and it's a solid. So the reason we have to go to a vacuum chamber and to do all this laser cooling is actually if we just put it in a cryogenic chamber, it just forms a solid, and it's very boring as a system. It actually explodes on us, but it's very boring. And then from this gas of 1 billion atoms, we send in many little lasers that forms like a little potential well where individual atoms can fall into and get trapped. And so this is a picture when we have many of these little wells, that a dark spot is a single atom. A not dark spot is with nothing. And so actually, if I have 2 atoms here, they form a molecule and we lose them. So we start with this kind of random array, which is bad for computing. And so we then move things around to get a perfect registrar or perfect array by just seeing where the atoms are and kind of telling them where to go. And then with this, what can you do? So these atoms, we've worked really hard to get them not to talk to each other, to not form molecules. And so all you can really do is like branding. You can make pictures, and that's about it. And so to get some really new physics out of it, you have to do something else. So we make superatoms, or these Rydberg states, which is basically you take the atom in the state that it wants to be in and use some lasers and excite it up almost to the point of ionization and have it be in a really high electronic orbital. So for rubidium, we normally sit at n equals 5. With these lasers, we go to n equals 62. The size goes from about 1/4 of an angstrom to about 300 nanometers, so it's 1,000 times bigger. I'll go through these last slide or two very quickly. If I think of the nucleus, which has a positive charge, and then this one electron, which has a negative charge, what I get is something called an electric dipole at that moment. And it turns out that it's a lot bigger in this Rydberg state. and you can get something called dipole-dipole interactions. So you don't necessarily need to know what this equation means, but it's the same thing you would experience just with bar magnets. If you have some magnets on your fridge and you kind of bring them together side to side, they repel, head to tail, they attract, and it's governed by the same kind of equation here. We take our atoms, and they should have this kind of interaction. It turns out they don't. I showed you the wave nature of the electron before. In these states that they live in, something like the ground state of hydrogen, it actually is in a kind of electron orbital where it's delocalized all over space. And if I think about the dipole of the nucleus with this electron, it's actually kind of pointing in all different directions and cancels out. So you get something else, you get something that's maybe more famous, van der Waals interactions or London dispersion forces. And it turns out that this is boring for us, but it's actually really important. So there are quantum computing companies that use this. They just got $230 million from Google, so it's actually quite useful for them. And then for us, we instead use multiple levels where the atoms act instead like little antennas. And so if I have different orbitals with different symmetry, one of these states can actually emit a photon, and the other state can absorb the photon. And so I should really think of this as an array of little antennas where light can sort of move around between the atoms through what are called dipole-dipole interactions. Okay, this is a picture of basically a photon moving around between two atoms. This is data where we look at them and start with a photon on the right, then this up state, and have it go back and forth between two atoms. So I think I'm almost out of time. I'll maybe just flash that. Okay, once you have this array, you can then study, you can ask like, what kind of physics, what kind of new phenomena does it support? It turns out that this model where you have particles exchanging photons between different resonators, it maps onto a kind of magnetic model. So just in the same way we get magnetism in real materials, this system looks like it should have magnetic properties. So if these interactions are large, in its ground state, which means in equilibrium, it should maybe form something like a ferromagnet. This is just like a chunk of magnetized material. And so we call this the ground state. In real life, this is just what happens at room temperature. In our system, we basically have to cool it down to get to these regimes. This is a picture of some magnetic correlations of one of these ferromagnets. Great. And then it turns out that if you put them instead of on a square lattice, something like this called a Kagame lattice, they actually shouldn't order in the same way they do for this ferromagnet, and they should form something called a quantum spin liquid. This is a funny state of matter that stays kind of like a liquid, meaning disordered, even at zero temperature. And it has neat properties. There are these chiral spin liquids actually predicted in this case that look a lot like the states that Jinendra Jain helped to kind of elucidate decades ago. This is an artist's depiction. And then for sake of time, I'll kind of go through this very quickly. But most of our experiments actually involve studying dynamics of these systems, something hard to do in electronic matter because things are so fast. Here we can start out of equilibrium and just see how our particles kind of move around the system. And we can use this to actually generate squeeze states, the same kind of things that were generated at LIGO. But here, that might be useful for sensing electric fields or maybe even dark matter. Some work done by students Chenzi, Xiang, and Mingsheng. A recent work by Ethan, where you actually take the same kind of system and perturb it a little bit, and you can study some dynamics that looks a lot like things that happen in superconductors, something called Josephson oscillations. And then you can go beyond two states to things that don't really have analogs in real materials. So electrons have spin up and spin down. We actually have many, many Rydberg states or Rydberg states of these atoms. And you can create things that have maybe 5 internal levels and study the dynamics and see things that kind of have never been seen in the lab before, don't appear naturally in nature, but can be made in these artificial quantum materials. This is some nice work by Matt, studying things called quantum membranes, which looks like sort of magnets if you had way more than 2 states. Okay, and with that, I'll maybe just quickly summarize. So the control of quantum systems is really rapidly advancing. So things that seemed like science fiction years ago are kind of coming into reality. And these synthetic quantum materials that you definitely can't hold in your hand like you would the semiconductors in an iPhone are starting to have a real world impact. And this is maybe just for people thinking about going into it, there's less kind of moral baggage, I think, compared to things like AI, which are also very interesting, in that, you know, our quantum computers, our quantum systems might have real world impact, but they're far less likely, I think, to take over humanity.
Thank you, Bryce. That was great. Now, Danielle, if you're ready, I could talk more, but if you're ready, we will pass it on to you because I think people would rather hear from you than me.
All right, so my name is Danielle Reifsnyder Hickey, and I'm thrilled to be here to talk with you all today. I'll be delivering a talk called Utilizing Electron Microscopy to Reveal the Atomic Frontier. So thank you so much to the organizers and to Bryce and to Abe. This is a wonderful opportunity to talk about what we do and talk about our excitement and hopefully get somebody excited as well. Okay, so the first thing, happy Valentine's Day. I love the pink shirt in the middle. Thank you so much for being here today. So today's presentation, this is a presentation about materials, but I'll spin it a little differently. I'll say it's a presentation about love, a presentation about flowers, presentation with diamond, and with maybe chocolate. So, and finally, materials. I'll start the story in Philadelphia, the city of brotherly love. So this is where I did my PhD. At the time, I was super excited about chemistry. I'd fallen in love with chemistry. I was starting to fall in love with materials because of these. So these are solutions that when you shine a light on them, they emit all kinds of bright colors and they fluoresce. These are known as quantum dots. Turns out that all of these are exactly the same material, but they're just in different sizes. So you can shine light on them and you get these different colors coming out according to the size. You synthesize them in solution. It turns out my PhD advisor actually did this foundational work that led to his PhD mentor getting the Nobel Prize just recently, which I think I'm glad I didn't know that at the time because it would have been a lot of pressure as a grad student, but that's a very exciting thing. So, and now we've come so far that materials like this are in television displays and commercialized in different areas. So starting with the background as a chemist, getting really excited about solid state materials and their properties and what they can do led to a lot of interesting things along the way. And so quantum dots are small crystallites. They're small, small pieces of crystals. Crystals are fascinating. They can come in all different shapes and sizes. They can be made of all different elements. They can have all different properties. But I was getting really curious what's inside them. We could detect the crystallites. We could measure their optical properties, what light they absorb, what light they emit, different things about them. But I was just really curious. The atoms inside them, they can drive the subtle things and sometimes the big things about their properties. So I wanted to know more. And so when we think about a crystal, and Bryce talked some about this in a different type of system, we think about some ordered array of atoms. Here they're chocolate hearts in honor of Valentine's Day, but you can see that you have some regular arrangement of the atoms in the structure, but you can also have defects. Here, all of these chocolate ones look similar except the one in the middle, which is different somehow. And it turns out to understand materials on the length scale of individual atoms, you need something called electron microscopy. So to see something this small, we really need to use a different kind of microscope. Looking at the outside these days doesn't tell you very much about it, but if I stood next to it, I'd probably be about that tall. So it's probably at least a couple of me tall. It takes up a whole big room. And inside what you have is an electron beam that's interacting with a very thin material and giving you all sorts of signals, maybe a diffraction pattern, maybe elemental information, different types of images. A really exciting technique. So when we think about how we're going to understand the structures of materials, we can take a step back and we can think about how images are formed by the human eye. So this is something we all have, something that maybe we think about if we get our eyes checked, we get glasses or contacts. And you can see an example here showing normal vision. So if you can see this candle here, you can see that there's a small image of this candle where it's actually upside down at the back of the eye. And in normal vision, what you expect is that whatever object you have here, you'll see an image of it right at the back of the eye. Of course, the eye isn't always perfect, so you can have different conditions. So myopia, anybody in the audience have that? Probably a few. So this is also called nearsightedness, and this is when you're over-focused and you focus and you see your object closer than you expect. Hyperopia, there's a name for that. It's farsightedness. Anyone in the audience? Maybe a few, yep. So another case when you're under focused and your image is not happening right at the back of the eye, but is past that. And then there's another condition that maybe some of you have or have heard of, astigmatism, where again, your image isn't forming perfectly. You actually have different focal points and it's blurring out your image. So as we think about how we can understand the atoms in a system, we want to think about these effects, and we can take advantage of these effects, and in fact we do very frequently. So maybe a number of you have seen or worked with an optical microscope at some point in your lives, where you could take some material and you could take advantage of the light that we see every day. So white light, you can shine on a material and you can get images of it, but only down to a certain length scale that's similar to the wavelength of the light. But it turns out we can take advantage of similar principles using an electron microscope. So an electron microscope has a lot of characteristics like a light microscope, but in this case, instead of a beam of light, we have a beam of electrons. And you can see there are all kinds of lenses and different components to it that help to form images and diffraction patterns. But we can really use this to start to understand things down to really small length scales. They're not perfect though. So it's been said that a top-of-the-line lens from an electron microscope could rightly be compared to using the bottom of a Coca-Cola bottle as a lens for light microscopy. So that wouldn't be too good. You would see a lot of smearing and blurring in your image. And then this other comment that if the lenses in your eyes were, let's say, only as good as our best electromagnetic lens, then you'd be legally blind. So we're trying to see really small things in an electron microscope. That doesn't sound like it's really going to get us there, right? We're going to see something blurry. We can see things on smaller length scales, but we're not there yet. So there's a lot of development that's gone on to make really powerful electron microscopes, and these have been recognized by some really substantial prizes. So in 1986, the Nobel Prize in Physics was awarded to Ernst Ruska for his fundamental work on electron optics and for designing the first electron microscope. So really, really pivotal discoveries and technology there. More recently, in 2020, the Kavli Prize in Nanoscience was given to these four gentlemen. And this is what really brought us into the modern era of electron microscopy, where we can see things at the sub-angstrom scale. We can see things at atomic scale and very small distortions. And then to highlight the impact of techniques like electron microscopy and specifically transmission electron microscopy, in 2017, the Nobel Prize in Chemistry was awarded to these gentlemen for developing cryo-electron microscopy for the high-resolution structure determination of biomolecules in solution. So often we're looking at crystals or things that are arrays of atoms that make up a solid material. That's a very well-ordered structure. But biomolecules, which are much more delicate and may not be as ordered, when you freeze them, you can also get lots and lots of information. And so using an electron microscope is really powerful for all of these things. The other thing I'd like to highlight here is the fields in which these prizes were given. So starting in physics, over here in chemistry, in nanoscience, developing the microscopes, understanding chemistry and materials and all these different systems of interest really crosses a lot of disciplines. And what do we do today? So today we have an electron microscope. If we look inside, it might look something like this. This is one of the high-end ones we have on campus here. And then this is a student driving it. This is Gabriel Vazquez-Lizardi, a graduate student in my research group. This is a picture taken when he was awarded a Department of Energy fellowship for some of the exciting things he's doing. And so we have these powerful microscopes and great people to work on them. And so what we're going to do is we're going to look to see the atomic structure of materials and how that can impact the properties. So what are some of the things that could affect? So all kinds of electronics. So Bryce started to talk about some of this, but devices such as smartphones, tablets, computers, the electronics in your car, anytime you're streaming video. There's a lot of talk about AI, artificial intelligence. All of these things need really powerful electronics. And they all depend on making better and better materials that will improve the electronic properties. But what I'd like to emphasize here is that atomic defects will often drive the electronic behavior of materials. So we really need that information. And so what kinds of things can we learn? So first we can just visualize the atoms, which is really exciting. So we can see where are they, how are they connected? And then we can do things like we can look at patterns in them, and we can even use AI and things like machine learning to understand precisely what the positions are and how they're related. We can look at things like interfaces. So here we can see something where there's coherent epitaxy, which means that two materials with the same crystal structure are grown right on top of each other, but the elements are different. So we have two elements down here and two different elements up there. So we can really understand precisely the positions of these atoms and how they're connected. And what's really exciting is that Penn State has recently invested in a brand new aberration-corrected TEM, which we call the Spectra. So we've been doing great things already, but we're really stepping into a new era with exciting instrumentation on campus. So we can look at lots of different things. We can look at the ordering of atoms in different structures. This is another one of my grad students, Sahani, and she's taking certain materials and looking at these highly ordered structures. Here you have a two-dimensional material where you have covalent bonding in the plane and some van der Waals bonding between these different layers. We can look at electron diffraction patterns that give us also lots of information about the materials. And then Sarah and Samuel from my group have been making some different nanomaterials, and we can look at their atomic structures. We can also look at their ordering and how they self-assemble. So in this case, we have nanoplatelets that have stacked into these really tight rolls, which some people have likened to maybe a roll of poker chips, a stack of poker chips. And we can use imaging, but we can also use electron diffraction to get a lot of information about the very precise orientation and self-assembly behavior of these materials. And things like this are important because even in nature, you can find differences in the stacking of materials. And so something like this could give rise to the opalescent properties of a material like mother of pearl. So we can also, one of the things that we can do is we can also identify not only the individual atoms, but the different layers in materials. So this was flipping through different thicknesses of a quantum material called tungsten ditelluride. This is work done by my student Nikolov, who's here in the audience today. Hi. What happens in this material is when we have a monolayer of it and we're looking from the top down, we can very clearly see the individual atoms. But as soon as we get to a thicker material, we have overlaps between those positions and they're much harder to distinguish. But what we can do is we can think about the structure and think about how we build it up from a single layer to a second layer, a third or fourth. And you can look at the different sites and say, okay, each of these is really one more atom being added, and that's giving rise to these contrast changes. So we're sensitive not just to the overall structure, but to single atom changes within the structure that are going to impact the properties. And for this material in particular, whether you have one layer or two or three or more drastically changes the properties and what it can do. We can do lots of analysis by ourselves with our eyes, right? We can look and see what we detect qualitatively. We can do peak fitting and extract some quantitative information. But we can also use more advanced big data techniques like machine learning to try to pick out patterns and trends that are much more subtle that our eyes don't detect well. So when this was flipping through, you might have noticed that it looks pretty similar at each thickness, but there's sort of an oscillation of intensity in certain columns. These are small things that we can sometimes detect by eye, but sometimes need more advanced techniques. So another area that my group is really active in that I'd like to mention today is called convergence research. So the convergence of materials and life sciences. This is actually a recent highlight from the Materials Research Institute of one of the graduate students in my lab, Jessica Thompson. So she has been working a lot with the TEM and techniques like the focused ion beam that I'll talk more about, and specifically doing cryo-focused ion beam or cryo-FIB. This is one of the techniques that came out of the material science community and has become really important recently for the biological community to understand the structures of all types of biomaterials and structures. And now has there are recent advances in the technique that are coming back to materials and going back and forth between biology and materials to be able to do very new and different things. And she's been working with the Materials Characterization Laboratory and with the Huck Institutes of the Life Sciences to really develop these techniques and do really exciting hands-on things beyond just the scope of what a regular grad student would do. So this is a really exciting area. And what can we do with this? We can do things with materials, but we can also we can investigate biomaterials. So this is looking at a bacterium. We can look at different cells. We can look at things like polymers. So these are materials that we've sliced into using something like focused ion beam microscopy. We'll take a material, we'll freeze it. So when the Nobel Prize was awarded for cryo-electron microscopy, part of the advance was learning how to freeze materials very rapidly so that they are what's called vitreous or glassy. They're not crystalline. They don't have a regular repeating structure. And this allows you to then see the native structure of your material, especially your biomaterial. So we have these fancy techniques that we're able to use, and we get really interesting information about the ordering. So in this polymer, you see different types of nanostructure and microstructure in the materials. And so one of the recent advances in using focused ion beam microscopy is using a plasma source. So this is an example of the instrument. This is one that can be run at cryogenic temperature, so it's great for biology and soft materials like polymers and a range of other sensitive materials. But what's special about it is that the ion beam that we can use to actually slice into the material or cut the material is a plasma source. So these are examples of different elements that can form that plasma source. And if you've ever seen a plasma, it often glows very brightly. And with this, we can do biologically targeted research, but we can also move into, I promised you diamonds, right? So we can also move into things that are quantum materials. So diamond is something that's been very interesting recently in terms of looking at the energy states and anomalies based on really small atomic point defects in the structure. So we can slice into that material and we can really thin it down in different ways with different chemistries and then start to get information about what we see in there. And we're just at the beginning of this. This is ongoing. There are a lot more things we hope to learn. But this is a great example of showing where we can take technology that's been developed and built for more materials problems, has been transferred to the life sciences and developed in other ways much more targeted toward the needs of that community, and then is coming back to the materials community. And again, just highlighting the great instrumentation we have and how fortunate we are, with the leadership here to really be forward thinking and invest in these sorts of things. Penn State also has a brand new plasma cryofib, which we call the Hydra. So the focused ion beam is great for biological materials. It's great for very hard materials like diamond that we want to understand at the atomic scale. But we're also really interested in two-dimensional materials. So I mentioned one earlier. This is an example of a flake of the two-dimensional material tungsten disulfide that's grown onto some bulk substrate. So we have some chunk of material that you can hold in your hand. If you've ever heard of a silicon wafer, it's kind of like that. And then we can grow these very thin and delicate layers on the surface. If you look at the a crystal model of the atomic structure, you can see the bulk substrate would be very large down here and is these atoms here. This has a couple layers of the two-dimensional material graphene on it, and then tungsten sulfide and can be multi-layer. This is an image from the TEM at low magnification where you can see this multi-layer structure and these terraces in the material. And what's really exciting is some of the techniques we're using with the focused ion beam, we're able to actually go in and just slice off a very thin layer of the top to localize just this material on top and a tiny bit of the substrate and get really, really high resolution imaging of these materials so we can understand them in detail and what kinds of defects they have. This is showing some detail about the layers and how they're stacked. I won't go into all the details, but in layered materials, this is really essential. Understanding where are the atoms, how are the layers stacked, how many layers are there, it can really drastically change the properties. One of the ways that we protect these materials so we can extract them and study them is we actually use 3D microprinting, and we have a patent pending on this, where we can make these arrays of structures. Here's some more chocolate for us. So looking at these really well-ordered arrays of materials that we can take and protect really delicate surfaces of materials. And then get really interesting information. So this is not an image, this is a diffraction pattern, looking at what we call reciprocal space or diffraction space. And you can start to see these sort of flowered shaped structures that are telling us that we actually have multiple crystal structures stacked on top of each other. And we can do measurements of that to understand exactly how they're arranged and what we can understand from that. So we've got some chocolate, we've got some flowers, thinking about our arrays that we 3D print and the types of structures that we start to see. I've talked a fair amount about 2D materials and how we can have these flat layers of materials that are very interesting for their properties as they get very, very thin. We can also have materials that are one-dimensional. So this is some work by a student, Cullen, in my lab. Actually, this is just a photograph of some art I saw in a museum recently. So there's this box that was on display. It has this really interesting pattern on the surface that's called a chrysanthemum and scroll design on the box. And if you zoom in, you can see these little flowers with the sort of scroll around it. And when Cullen was studying one of the materials he's been looking at recently at atomic resolution to understand how is the material built, what sorts of defects are there, can we see phase transitions between different crystalline phases, he saw these really interesting patterns that correlate to the crystal structure that we see. And so this, looks sort of like a flower shape like we see in the art here, But what we see is that actually each of these units is a one-dimensional chain that goes through the crystal structure. And so that will really affect how electrons move through a material, how you can convert between different phases. And this is the type of information that you can't get unless you're doing electron microscopy down to the atomic scale. And this is a material, interestingly enough, that we grow in a solution. It actually comes out as these bulk crystals that we can then study. And so thinking about the structures that we find, sometimes they're expected, like I showed, I guess in this last slide, I showed a crystal model of what we expect of the structure. But other times we see things about how materials are connected. This is an interface between two crystalline grains. And we can see that there are these steps at the interface because of the angle we form here and the stability of the system. And what we see is these steps are related to these, I'll call them flower motifs, this eightfold 1D unit that's going into the plane of the page. And when we compare this to something that we see in an artistic representation of a repeating pattern like this, we see that when you make the art itself, you can stop these wherever you want. So you can have this full flower in this repeating array, and when you get to the edge, you can just make half of one, and it stops at that boundary. In reality, in a system, you have to think about what is going to chemically be stable. So is it going to be stable to just stop halfway through a structure, or do you need to form each of these units independently and fully to then form that junction between the material? So when we think about something in art, we're not constrained with chemical stability, but we are able to design it as we wish. And when we think about materials and designing them, we're thinking about how would we like to build a material, but also, how do we take into account the stability of the chemistry of it? And this is Culina doing an outreach activity with some local kids. Okay, so what I hope I've shown you today is some what I think are interesting snapshots of the kinds of work we're doing using electron microscopy to really answer questions down to the atomic scale. And so what I'd like to leave you with as some thoughts are just that understanding materials at the atomic scale is really important. It's going to help us design new materials, design materials with emergent properties that are going to do things differently. So, we think about all of the data we're consuming these days, all of the electronics we enjoy, for leisure or that are integral to our work and our, getting around in our life. It's going to be really, really important that we keep improving electronics and we keep designing new materials that can do better. And one of the ways to do this is to keep pushing the advances in instrumentation. So I talked about some of the fantastic and fancy new instruments we have here on campus that my research group is really excited to be using. And these are leading to new ways to ask and answer questions and to fundamentally understand how are these atoms arranged. And I just also want to say this is a great time and place to be exploring the development of materials. There's a wonderful research community on campus and lots of exciting things happening. So a few references here. Of course, I'd like to acknowledge my group. So this is my research group. These are the graduate students working with me. Several of them were highlighted in this talk. The ones here are newer, so they haven't been in the group picture yet. They just joined. And then I'd like to thank a number of funding sources that have been really important to making this work happen. And then there's just one final thing. So is anybody a Penn State football fan? Or are we just Penn State science fans? Okay, more science fans than football. That's fine. I'm 100% okay with that. But what I would like to say is I heard a press conference from the newly hired football coach recently, Matt Campbell, and I really liked something he said. So I'll read this quote out loud. He said, "I believe in multiplicity. I think sometimes we get lost in the what are we? And what great teams are, what great offenses and defenses do, is they highlight the players and the playmakers on each side of the ball. And this really struck me because I think that, I'm trained as a chemist, I'm working in materials, we're talking about convergence with life sciences, we work with lots of physicists and engineers. We're just really excited about materials problems. And I think that in materials research, it really draws from all kinds of disciplines and different backgrounds contribute to it. And we need the best team and we need the best tools and the best attitude to succeed. And so if you're interested in being part of this, come join us. We're really excited about what we're doing and I'm really happy to be here talking with you all today. So there are a few chocolates up here. Hopefully at the end, some of you will come up and I'll get to meet you and have some conversation. So thank you so much.
All right, hello. I'm Matt. It's my pleasure and privilege to be moderating some questions from all of you. So first, Professor Reifsnyder. Hickey, thank you so much. This was a wonderful talk. Thank you, Professor Gadway, as well. It was really great to learn from you. It is time for questions, so please come up. So I have a couple while some are collected from you, so we don't have to wait. Why don't you come to the front? Yeah, sure. Okay, so first question. Tackling difficult problems takes a team. So can you please discuss some of the collaborations across institutions or disciplines that have helped you bring outside perspectives and talents to your projects? And you're going to need this.
Okay. Do you want to take this or?
Sure, I'm happy to. Yeah, so I have the mic still. So yeah, no, that's a great question. And what I would say is that there are all kinds of work environments, all kinds of institutions. This is a fantastic institution for working across disciplines. You know, as you can see, my research is interdisciplinary. I'm in 2 departments. I have lots of colleagues across departments. But just being close to, you know, physically close to lots of people who are excited about science and making new discoveries is amazing. Penn State has really, you know, there are opportunities for seed grants that help support the funding and specifically require that that faculty or researchers from different departments and different colleges are teaming together. So there are new ideas that have come up and new teams that I've been able to, you know, lead or be part of. Some of the acknowledgements I had were the Materials Research Institute, the Huck Institutes for Life Sciences, and I actually didn't write the College of Medicine, although those 3, you know, have funded seed grants in the past. There are collaborative research centers like the National Science Foundation Materials Research Science and Engineering Center, or MRSEC, that my group is part of. That is just a fantastic way to interact with lots of researchers across disciplines. And you know, 2 of my students are here today, Nicola and Wyatt. So they're excited about what we're doing. I'm happy that they're here today. So yeah, you want to comment on that too?
Yeah, I think our research is slightly less interdisciplinary. It's a vacuum system. We can't send it to other people to scatter off of, but we still have a team, and it's the team in the lab, meaning students and postdocs, is kind of the most important part. So getting good students like Matt and Ethan and good postdocs is super, super important in supporting them and having kind of good atmosphere. Science is more fun when you're doing it with each other. So having good colleagues like Dave and Marcos and Tom and lots of other friends, Jen and folks in the department to talk to and collaborate with is kind of the great thing. And so mostly we talk with theorists and kind of collaborate with theorists, both at Penn State and outside, and then talk to and commiserate with our experimental friends on lasers that die and things like that.
All right, thank you. And then I have another question. So Professor Reifsnyder Hickey's group images atoms that are lab-grown electronic crystals, and Professor Gadway's group images atoms that are precisely arranged optical traps. So with the broader goal of helping the scientific community understand quantum matter, how are your research questions and approaches complementary?
Think about that. Yeah.
Yeah.
I'll go ahead.
Sure.
So one thing I would say is that, you know, it's interesting to pair our research together like this because we're both interested in atoms and their properties and having some regular array in a crystal lattice. I think it's really interesting in Bryce's work using lasers to do that because with lasers, you're working with waves and the interference of waves, and you're able to get you know, as he mentioned, a perfect lattice in certain ways that when you grow a crystal, you get some of that, but you'll always have edges or grain boundaries or defects within the lattice that are the result of the growth. So in my group, we think a lot about not just the materials and their structure, but how they're made. You know, fundamentally, I come from chemistry. How do you make a material? How do you get it that way? What are the processes that get it there? What are the features of it after you make it? How does that feed into the application? So, you know, thinking about physical materials that you don't need a laser to trap, and thinking about all the imperfections that can result from how something's made. And sometimes you can take advantage of those imperfections. You can actually harness that for the properties and do something that's exciting. Other times you're really just trying to get rid of those defects. But having systems like Bryce's where the lasers are creating it gives you a very different type of control, so you can approach these questions in some different ways.
Yeah, and I can maybe looking at the perspective of sort of how physics and material science and sort of actually building materials have interplay. So I talked about how Louis de Broglie had, you know, posited the idea of matter waves, and just 3 years later, Davison and Germer at what became Bell Labs looked at electron diffraction, and then you see nice pictures from Danielle's lab where they're using LEAD, which is low energy electron diffraction.
SAD.
Maybe not
LEAD, but a different kind of electron.
LEAD similar, LEAD adjacent. to kind of like in situ look at how something's growing in real time to better develop materials. And so there's some latency from really beginning fundamental application or fundamental ideas to then applications that drive new research or drive new things that we all use in our everyday life. And then the things people are doing now with quantum computers and quantum simulation will eventually have certain, maybe help design new materials. So things that you can't exactly calculate that have some correlated properties, like high temperature superconductors that have the possibility to transform certain parts of society. We still don't understand them, and we maybe need these special purpose machines to actually solve problems that have been around since the 80s and before. Okay.
Thank you both. We have a lot of questions from the audience, and I'm going to do my best to do your good questions justice. If I happen to ask one the wrong way, please come up and talk afterwards. So I have a question for you, Bryce. When you produce a lattice of atoms, as shown in the presentation, do the atoms form a Bose-Einstein condensate, and how are van der Waals force between atoms controlled?
Yeah, good question. So there's kind of two flavors of these experiments. In some cases, if you get a bunch of atoms together, you take all the entropy or sort of randomness out of it. If you allow them to overlap or sort of go into one big well together, they can form a Bose-Einstein condensate just naturally. That's kind of what they do. It's sort of like you take a bunch of photons, particles of light, you get them to bunch up inside some thing called an optical cavity, and maybe they form a laser. And people have done that or are starting to do that in these kinds of systems where you create a perfect array and then you actually bring them together and you can get a small little Bose-Einstein condensate. In one of the pictures I showed you of our array, we had them together, and I showed a picture of something called an XY ferromagnet, which is actually, one can think of as a Bose-Einstein condensate, not of atoms, but of the excitations or the spin excitations of that system. And so there are ways where you can even make something like a BEC or Bose-Einstein condensate out of these photons that exchange between the atoms. And then in terms of controlling van der Waals interactions or these dipole-dipole interactions, you can change the distance between the atoms. You can play tricks with the lasers you're using to excite the atoms. And most of the time, we're actually playing our tricks with microwaves. So normally when we think about probing energy level transitions between atoms, you're shining in lasers or you're looking at light emitted optically. And in our system, when we're near this ionization threshold, these levels are actually pretty close to each other. So we're just sending in really long wavelength microwaves to coherently drive transitions. We can actually change the states. So in a material, the properties change if you shove atoms together. The orbitals change, they hybridize, and that's how you get band structure. In our system, you can actually just couple different states and take the levels that sort of nature gives you and make new levels out of them. So that's one way we control the way they interact.
Thank you. And then this is for you, Danielle. Do you think the use of AI and machine learning will revolutionize your field over the next decade? If so, how?
I think it will definitely be very important. So in terms of doing analysis of materials, there are all kinds of things that you can do as you start using these techniques. You can more precisely define what you have. You can more quickly identify what you have. You can identify, we have some recent work working to identify things that are not what you expect or not as regular as something you might put in as an input or a simulation. So there are all kinds of ways that I think it'll be very important for just understanding what you have and being able to be more flexible in terms of analyzing things that are unknown when you start. I think there's a lot of power there, and we have to figure out the ways it's really going to be the most impactful. But certainly, I mean, just watching how fast it's permeating everyday life and kind of how you search and what you find, and even when you're not trying to use it, it's embedded into the tools we use. I think it's going to it's everywhere already, and that's only going to grow. So we need to find the really specific ways it can help us. But I think yes, I mean with electron microscopy, things are getting more and more automated, and we're pushing more and more toward big data. We're able, with new detectors that have been developed, to just collect massive amounts of data at once that are way too much for one graduate student or one researcher to sit and manually analyze everything. So I think we're already taking advantage of these techniques, and we'll just keep developing how we can use them. But with so much data, we'll keep getting, we're getting higher resolution, we're getting faster timescales, we're able to collect a lot that's giving us more and more specific information about everything, and just loads of it that these techniques will be really important for handling.
Thank you. I believe our next question is referencing the interference and diffraction experiments that you highlighted. So this question is, what is the largest physical thing to be shown in more than one location at the same time? So what is like the largest thing that they saw quantum interference from, I believe?
For you.
Yeah. So there's different ways in which you can have these superpositions be kind of crazy. So for tiny things like atoms, an atom's pretty big, they've shown that it can be in a superposition over sort of meters with some debate, but everyone kind of believes centimeters, meaning I can just have something here and with some probability to also exist, I don't know, at Matt, maybe now, and nature doesn't cause it to collapse in some way. So there are questions about whether even just how gravity interacts differently can cause it to sort of like it almost performs a measurement on it. In terms of size, it's these sodium nanoclusters that people have created in Vienna, and it's 7,000 atoms, and I think it's about half as big as the smallest little virus you can make. So it's not crazy to imagine something much bigger. And then in some weird way, there are big things. So the mirrors at LIGO, when they send in squeezed light, in some way you can probably interpret as having some superposition. And there are small devices, things like cantilevers that vibrate, and they can be in quantum states. So that's another quantum big thing.
Thank you. Danielle, this question is for you. It's a series of questions. Why did you come to Penn State? And can you talk about Penn State's expertise in microscopy?
Sure. I came to Penn State because it's a huge and wonderful research community. It's a place where you can do great science, where you can easily work across disciplines, which is something that is very important to me. And I know there's a lot of innovation and discovery there. And in terms of the microscopy community, there is a lot happening. So I mentioned, we have brand new instrumentation that's really fantastic and cutting edge. We have several different faculty members who are using this instrumentation and just going to be using it more and more. So people who are leaders in different areas with two-dimensional materials and metals and nuclear materials and all kinds of different things. So I think this institution for a number of years has really valued electron microscopy and has worked hard to build up the instrumentation and the community. And there are just going to be some really exciting things happening in the near future. Yeah.
Thank you. As a direct follow-up, how many other universities and institutions, organizations have microscope technologies like Spectra and Hydra?
I can't give you a number.
Okay.
So the number is growing, but certainly it is unique to have capabilities at this level and multiple capabilities at this level. So, it's not just the Spectra, it's not just the Hydra, it's that we have, on the TEM side, we have multiple, we've had entry level and mid level, and then the Titan used to be our fanciest one. Now the Spectra is replacing that. We also have a Titan Krios, which is dedicated for liquid nitrogen temperature cryogenic experiments. So really important for biologists and sometimes crosses over into materials and chemistry as well. We also have, that's the highest level dedicated cryo instrument. We also have mid-level cryo instruments. We have a whole range of different scanning electron microscopes, so SEM instruments. We have multiple focused ion beam instruments, so a couple that operate just at primarily at room temperature, and then the Hydra, which is really, doesn't have to be cryo all the time, but is really good for cryo capabilities, and then has these new plasma sources that give it different capabilities for materials that, new materials challenges like larger areas or harder materials or different types of structures. So we, this is a fantastic environment to be in to do this kind of work. And if you're here and you're excited and you're looking to take advantage of all the capabilities, looking to put in the work and just, learn everything you can, become really expert level on them, this is a cool place to discover new science.
Thank you. That's a great answer. I have a two-part question I think both of you can answer. So can you use defects in crystals to make a material more useful? And said another way, can you design defects and manufacture them atom by atom? So,
Yeah.
So can you use defects and make them useful, and can you design them atom by atom? Yeah. So yeah, with defects, pretty much every material has defects. It's a question of, are they useful? So, anything that is electronics technology built on silicon is built on defects. So there are elements intentionally doped into the silicon to give it the properties it has. That's how we make things like transistors. That's how we make electronics that are going to, power everything that we can put in our back pocket or stick in our bag and then get video and data and all these things from. So yeah, so sometimes defects just happen from the growth method. Sometimes you're intentionally adding them to a structure because you know the properties they'll give. And when we're making new materials, we're always thinking about, how are they grown and what defects are there? So if you grow, we've done some study looking at the same material grown different ways. So you can grow a bulk crystal of something. So it will be a physical chunk that you could hold maybe in your hand or at least with a pair of tweezers. And it may have certain types of defects. If you grow the same material as a thin film grown on the surface of a substrate, it may have similar related defects. It may have totally different defects because now it can have grain boundaries. Now the stoichiometry of the precursors during the reaction is going to impact which elements go where and how they bond and react together. And then you can grow things other ways. You can grow them in solution. I showed some examples of growing things colloidally in a solution. You can also get some of these materials. And even if you have, you can start with a crystal model of something that you have on your computer that says, this is where the atoms should be. This is how they should bond. But then when you go make the material, yes, you have some of that, but then you'll be missing an atom, you'll have an extra atom, you'll have a cluster of atoms, you'll have a region where it's actually converting to another phase, you'll have a grain boundary where two crystals are joining together and the atomic structure ends up being different. So yeah, there are all kinds of ways you can design crystals and engineer them. And certainly when they grow, you're always looking at, what did you get and how does it impact the properties? And if you take that same growth method and tune those properties and change them up a bit, will you either have more or fewer of those defects that can then change your properties, or will you do something totally different to the structure that you didn't expect? Yeah, and there's great synergy here between people growing materials, characterizing materials, lots of theorists on campus working on these problems. So it's an interesting place to be in science.
And I can add how disorder comes in our artificial engineered systems where really nothing's random. There's maybe some thermal random motion, but we can really either make perfect optical crystals or put atoms wherever we like them. So in a kind of past current life, I study a lot of localization physics. This is things like Anderson localization that was predicted to be relevant to maybe real materials, but gets mucked up by interactions and phonons. And so you can study this in cold atoms. We studied in our lab or discovered something predicted actually by Janendra Jain, something called topological Anderson insulators, where you actually get something called topology from a certain kind of disorder you add to systems. And then one of our experiments now is building something called a quasi-crystal, which is somewhere between ordered and disordered, meaning if I imagine putting electrons in this kind of thing that led to a Nobel Prize back in from work in the 80s, they can have this Anderson localization, even though it has perfect rotational order, but has no translation symmetry you expect from like a regular crystal, from a normal crystal.
All right, thank you. This is a question about the double slit experiment. When you're sending only one electron at a time, what is interfering to form the light-dark pattern?
So the question is, what's interfering? It's basically a particle interfering with itself, different possibilities for where it could be. So it's we call these probability waves, and it's a very weird thing, but just imagine there's some probability wave associated with me going this way, and then we recombine and we travel a slightly different length on those two paths, such that when we show up, we have some different property. There's something that's sort of a little bit different about us. In this case, there's a what's called a phase difference, kind of like having a wave at its crest and a wave at its trough meet together, and you would find that those things cancel out or interfere, and so that's what's interfering in this case. And this happens even for light too. When I imagine just sending a laser through one of these interferometers like LIGO, it really is happening at the level of individual particles interfering. And you can see this by sending one photon in, but it's maybe just more impressive when you see it with massive particles that you don't expect to be waves.
All right, thank you. And then this is for you, Danielle. The interfaces, kind of like the flower-like material, they look kind of random. So interfaces materials are kind of random. How does that affect materials properties such as strength of a joint, for example?
Such as what?
The strength of a joint. Yeah.
Yeah. So When you have a crystal, you have the atoms arranged in a regular repeating array, this crystal structure. And this is actually something we've been talking about recently in my, my first year material science course I'm teaching, where depending on which orientation you look, you can define different planes of atoms, and some will be denser, will have more atoms on the plane than others. And so if you think about something like the mechanical stability or failure of a material, which direction you actually are interacting with a crystal can matter to how strong it is. And so when you have a material that is single crystalline, you're thinking about that regular, you define a unit cell, which is the smallest unit, you translate that in all the directions, and you build up this crystal. Then when you're thinking about its behavior, you're thinking about these crystal planes that are defined by the symmetry of that crystal lattice. When you get to a lot of real materials, you won't just have a single crystal, you'll have something that now has bits of single crystal connected, so something that becomes polycrystalline. This is where you'll have something like a grain boundary, like I was showing, where you have two crystalline regions and then they meet. And what happens is they don't meet coherently into one lattice, they have some misorientation. That then means that the atomic structure is different at that boundary. Often these boundaries will be weaker. So in chemistry, we like to talk about dangling bonds. So when you have a perfect crystalline lattice, every atom is bonded in just the way to its neighbors that it expects and is in some low energy favorable state. When you get to an edge of a crystal, or you have two crystals joining, now the atoms can't reach onto their neighbor exactly the way they expect and be the most stable. And so sometimes you'll have dangling bonds where the electronic condition is not satisfied, and then it's more reactive or more prone to damage. So when you think about grain boundaries, they certainly are important to mechanical stability, electronic structure. Do electrons move well through grain boundaries? Do they not? Do they scatter at a grain boundary? These are very important questions in these materials. Yeah.
Do we have time for one more question each, or just one more? One more. Okay. So, Danielle, this is for you again. Can you discuss how you make your samples to examine individual atomic layers?
Yeah, so we work with a variety of materials. Some we grow ourselves in the lab, and others we work with collaborators on campus. So to get a single atomic layer, that's usually in the case of a two-dimensional material. You can grow them colloidally like some of the things we grow, but more frequently you grow them as a bulk crystal or as a thin film on a substrate. And so on a substrate, you can introduce the different precursors and have them interact with the surface and move around and bond and form that single layer. When you grow something as a bulk crystal, so these layered structures in the plane will have covalent bonding, and then out of plane between the layers, they have just van der Waals bonding, which is another type of association, but not as strong. So what you can do is you can actually pull them apart with those layers. So a number of years ago, there was a Nobel Prize awarded for literally taking Scotch tape, putting it on a crystal of graphite, which is layers of carbon atoms, and pulling it off to exfoliate a single layer, which is then called graphene. So feels really low tech, but has really spawned a huge field and a lot of excitement and a lot of attention to how can you understand and make and study and get really amazing properties out of two-dimensional materials. Yeah, so thanks for all the questions.
All right. Well, thank you so much. Thank you, everybody, for coming.